So in this video, we're going to go through the process of analytically solving a linear, non-homogeneous, constant coefficient discrete equation, the one that you see on the left-hand side here. And now what makes this linear is the fact that all of the dependent variable terms, the xn plus 1 and the xn, that they're raised to the first power only, or that the equation is quote-unquote linear in them. We're not multiplying those dependent variables together in any way. The dependent variable is really just showing up as a constant times a dependent variable to the first power. What makes it non-homogeneous is the fact that we have these extra terms in the equation that have no dependent variables attached to them. And it's constant coefficient because in front of all the dependent variable terms, we only have constant values like this minus 2 over 3 or a factor of 1 in front there. Now, for this problem, there are three general steps in how we go about the solution. The first thing that we'll do is find what we call the general solution or the complementary solution, and this is going to be the solution that solves the homogeneous problem. From there, we're going to look for a particular solution using the method of undetermined coefficients, and this will be the solution that actually solves the non-homogeneous equation that we see here. And then finally, we'll recombine in the last step, and finally then use the initial values to find all of the unknown constants in our solution. So let's begin by finding the general solution or the complementary solution. So when we look for the general solution or complementary solution, basically what we're looking for is the solution to the homogeneous problem. So we're looking to solve the following equation. Xn plus 1 equals minus 2 over 3 times xn. And now when we look at this is, of course, is linear, it is homogeneous, and constant coefficient. We can try a particular solution guess or solution ansatz here, where we assume that xn equals some constant value raised to the nth power. So what we're going to do is take that solution guess and basically put it or substitute it into our equation. So for example, what we'll do is in a moment, we will take this xn or this lambda to the n and substitute into the xn in our equation here. Now you might be wondering, how do we handle this xn plus 1 on the left-hand side? Well, basically we just iterate our solution guess. So if we iterate our solution guess, xn plus 1 is going to be, well, that constant lambda we're going to solve for, just raised to the n plus first power. So we'll take that xn plus 1 and basically substitute that into the left-hand side of our equation. So let's go ahead and do that now. So on the left side of the equation, after we substitute, we'll get the following. We'll get a lambda raised to the n plus first on the left. Now on the right side, we still have that factor of minus 2 over 3 in front, but then when we substitute in for xn, we get that is that lambda that we'll solve for momentarily raised to the nth power. So at this junction, what we have left to do is actually figure out what that lambda value is. So we get to do a little bit of algebra. So we can subtract the right-hand side. So we get lambda to the n plus first plus 2 over 3 times lambda to the n equals 0. We can factor out a common factor of lambda to the n from both of these terms, and finally get lambda plus 2 over 3 equals 0. So we find that there's two different or a couple different values of lambda that satisfy this equation. We have the so-called trivial solution on the left side, that lambda equals 0. Again, we just call this trivial because if lambda equals 0, going back to our solution form up above, our solution is just identically 0 in this case. Now this right-hand side, we have what is called the characteristic equation or characteristic polynomial, and that'll give us the lambda values that'll be a little more useful for our solution. They'll be the non-zero values. So we get, in this case, when we solve the characteristic equation, we get lambda equals minus 2 over 3. So why this is useful is, well, what this then tells us is that our general solution or homogeneous, homogeneous solution in this case is our xn is equal to lambda, which we found is minus 2 over 3 raised to the nth power. Now, because this equation is linear, What that means is if we had multiple lambda values, which we don't in this case, we could just keep adding on terms in a linear fashion, as in we have this lambda to the n, we could add another lambda to the n. But the other thing I want to mention is at this point, because of the linearity, we also can put an unknown constant factor in front, say a constant factor of c. And that will be our general solution or complementary solution that we'll use towards the end of the problem. So we'll come back to this in a little bit. The next part is, well, once we have that general solution, we're not going to figure out what C is using the initial value yet. We're going to move to instead computing the particular solution. And the particular solution is going to be the solution that solves the non-homogeneous equation as stated here. So what we look for in this method is basically we're going to use what's called the method of undetermined coefficients. We're going to look at what the non-homogeneous term looks like in our equation. So in this case, it's really the 4 minus the 2e to the minus n. And we're going to try and guess a solution of the same form. So let's just pick out a couple things. This is some constant. So when we guess a particular solution, which I'll just denote xnp, we're going to need a constant in there, which I'll just call a. And then if we look at what else is in this non-homogeneous term, well, this is some exponential e to the minus n with a factor in front. So basically, we have an exponential type form. So we can also add to our particular solution some unknown constant coefficient b that we'll solve for momentarily, times the exponential that we see there. And what the name of the game is at this junction is we're going to substitute in this guess for a particular solution everywhere we have the dependent variable in the non-homogeneous equation. So for example, you can see that, well, we're basically going to take that and put it into the, substitute that into the xn. But we also need to, just like we did before, substitute in for the xn plus 1. So you can imagine we can iterate this particular solution just like we did with the non-homogeneous solution as well when we're solving for that. And we'll have that this is now a plus b e to the minus n plus 1. All right, so those two things we can substitute into our equation. Again, for the xn plus 1, we'll substitute that into the left-hand side for the xn plus 1. And for the xnp, or the particular solution, we'll substitute that into the right-hand side. And the non-homogeneous term, we're basically going to leave as it is, and that's going to help us figure out what these unknown constant values are. All right, so let's go ahead and do the substitution. So on the left, we have a plus b, e to the minus n, and then e to the minus 1 when we distribute the minus 1 into that power. On the right-hand side, what we have is minus 2 over 3 times a plus b e to the minus n, and then plus the original non-homogeneous terms, 4 minus 2e to the minus n. Right. So I'm just going to multiply everything out. So we have a plus b e to the minus n times, still this e to the minus first. It equals minus 2 over 3 times a minus 2 over 3 times b e to the minus n plus 4 minus 2e to the minus n. And what we're going to do next is basically ask ourselves, what terms have exponentials attached to them on the left and right side? What terms don't have exponentials attached to them on the left and right side? As in, what terms are only constants? So this is a similar process to how we build up some systems of equations before. You might recognize from things like partial fractions or maybe some other mathematics courses. But if we look first, let's say, what are all the terms that have an exponential attached to them? On the left side, that would be that second term, b e to the minus n, e to the minus first. So if we're asking all the coefficients on that, what it is, we have a b times e to the minus first. Now on the right side, when we do a similar thing, that would be this exponential term that has a factor of, in this case, minus 2 over 3 times b attached to it. And we also have this second term, the minus 2 times e to the n. So the constant that we would need, or the coefficient, is the minus 2. Now we can do the same thing for the constant terms on the left and right side. If we look at what the constant terms are on the left and right side, well, on the left side, it's just whatever this a value is. And on the right side, it is the minus 2 over 3 in front of that a, as well as this plus 4. Oops, I forgot the a down below. So again, we're trying to build up a system of equations to solve for our two unknowns in that way. So it looks like from both of these equations, we have one equation fully in terms of a, another equation fully in terms of b, that we can go ahead and solve for these. So let's go ahead and just do a little bit of algebra. So if I call this equation 1 and equation 2, basically what we're going to do is take equation 1 and solve it for b. So let's go ahead and just do that first. So what this looks like is on the left side, we have b over e to the first, or b over e, is equal to minus 2 over 3 times b minus 2. So what it looks like we should do is collect all the b's on one side, factor a b out, and solve for it. So let's add 2 over 3b to both sides. And we have that's equal to minus 2. So let's find some common denominators here, which looks like 3e is the common denominator. So we have 3b plus 2e all over 3e times b, oops, forgot to put the b in the second one, is equal to minus 2. So from this, we can factor out a b from both of these terms. And this looks like we have a 3 plus 2e all over 3e is equal to minus 2. So from here, we can figure out what b is just by dividing that factor on both sides. So we have b is equal to 3e all over 3 plus 2e all times minus 2. Some constant that we can use later. So this is minus 6e all over 3 plus 2e. So we'll come back to this in a bit. Let's not forget about it. But we found the constant factor in our particular solution. Next, we can figure out from the second equation, so number 2, solve the second equation for a. So we have a is equal to minus 2 over 3a plus 4. So we can add 2 over 3a to both sides. Factor out an a, get 1 plus 2 over 3. That gives us a 5 over 3 is equal to 4. And we can divide both sides by 5/3. So we get that a is equal to 12 over 5. So what's useful about this is now we have our particular solution. So xnp is 12 over 5 plus this factor of b, which is minus 6e, all over 3 plus 2e, all times e to the minus n. So we have our particular solution now. And the next step for us is going to be, well, taking our particular solution, adding it to our homogeneous solution or the complementary or general solution, and then use our initial data to find the unknown constant in our general solution. So I'll just say this is part 3. Combine and use initial data. So our full solution, xn, should be equal to the solution we get from the general, which was the homogeneous solution, and our particular solution that we just solved for through the non-homogeneous equation. So if we go back, our general solution was c times minus 2 over 3 raised to the nth power, and our particular solution is the one sitting up above, the 12 over 5 plus this constant times e to the minus n. So again, this was our general solution or the complementary solution that solved our homogeneous equation. And this second piece was our particular solution that solved the non-homogeneous equation. And the thing to point out right now is that from the general solution, we have this extra constant c that we still haven't solved for. And we're going to be able to tie this entire solution into our initial values, or by using our initial values to land us at the correct starting place for this whole discrete system. So our initial data, or initial value, was the following. It was that when x or n equals 0, we start off at 1. So we'll take the following, our solution above, and just plug in when n equals 0 into it. So we get that this is equal to c times minus 2 over 3, now raised to the 0, plus 12 over 5, plus this factor of minus 6e, all over 3 plus 2e, times e to the, well, minus 0 or 0. So this thing's going to simplify for us a little bit. But again, from our initial condition is when n equals 1, x0 equals 1. So we set that equal to 1. Okay? So what we have still is c plus 12 over 5 plus this additional constant minus 6e all over 3 plus 2e. And what we need to do is solve for, well, you guessed it, what c is. So we get that c is equal to 1 minus 12 over 5 plus 6e all over 3 plus 2e. So we can take that value of c and substitute it into our full solution. So we finally have that the full solution xn is equal to this value of c, 1 minus 12 over 5 plus 6e all over 3 plus 2e, times minus 2 over 3 raised to the nth power, plus 12 over 5, plus this constant, minus 6e all over 3 plus 2e times our decaying exponential e to the minus n. And that would be our final solution in this problem.